Now, at this point, things seem strange because as we keep adding more numbers into our sets, it just seems that they're the same size. Because remember, all we need to do is find a one-to-one correspondence between one element and another element of all elements in both sets, and therefore they're the same size. The question that I left you with is the size of the rational numbers equal to the size of the natural numbers? If it is, there's only one infinity, and life's good, and we can just say it equals infinity. If it isn't, then things get really weird, because then that means there's not just one infinity. There's a lot of infinities. There's an infinite number of infinities, and even that is, you have to ask, well, what does it mean by there's an infinite number of infinities? Is that infinite? Well, before I jump the gun, let's go and do a proof by contradiction, that idea of assuming something, coming down to a contradiction, and therefore suggesting that whatever it was we initially assumed must be wrong, and the opposite of it, therefore, must be true. So let's assume that this is true. Then this means that any real number, any number, whether it's rational, irrational, doesn't matter, can be put in a one-to-one correspondence with the natural numbers. Put simply, it means that I can write a whole list of numbers one by one in a row, even though it's going to be infinite. If I had an infinite amount of time and infinite amount of space, I could theoretically write every single number that's out there on a piece of paper, if it's true that these two sets are the same size. So let's assume that, okay? And what we're going to do is we're going to start with an arbitrary number. Okay, let's start with the number 0.1. And what I'm going to try to do is list all the numbers, okay? And what we're going to do is construct a new number based on the previous number. So I'm going to map this to the number 1. Map this to the number 2. I'm going to create a new number, and here's how we do it. We keep the same number. I'm sorry. What we do is we choose a new number that is not in the that is not the number in the same decimal here. Okay, so and then you can choose an arbitrary number, and you can just keep doing this, right? So let's assume that we have 1 second. Sorry. Something is not working correctly with my pen. Yeah, sorry. Okay, now it looks like I'm okay. Sorry, I lost my thought. Let me start over here. So assume that we have a mapping, right? Assume that we can list every single number. And if we can list every single number, let's just choose a few numbers in this list. That is, suppose we have a list of all the numbers. We're alleging that every number that we have is in this list, and so on and so forth, right? I just chose arbitrary numbers. And suppose we put it in decimal form. This is 6, by the way. The question is, can I construct a number that's not in this list? Because if I can, the two sets are not the same size, because I reach a contradiction. So let's see if I can do that, right? Let's let's construct a number 1. So what we're going to do is construct a new number, and we're going to say, okay, that new number, we're going to basically put in its decimal point a number that's different than the decimal point that we're on for that particular count. So we're going to go decimal point by decimal point. So, for example, the number 1 is here. Let's create a new number. Let's say 0.2. Okay. 0.2 is clearly not in this list so far because this is 0.1 and 0.2 is different than 1. So therefore, this whatever number we're constructing can't be accounted for by this number in our list, our alleged list of every single possible number. So let's go to the next number, right? The next number, let's look at the next digit here, which is 6. Let's pick a different digit, 7. Clearly, this number is not in here because 7 is different than 6. Let's move to the next number. The third digit is 1. Let's choose a different digit. It can be anything random, doesn't matter. 5. We see that 5 is not the same as 1, so this number cannot account for our number. What about 6? Let's choose a different number. 8. 8 is different than 6, so this number, therefore, cannot account for our number. And you'll see that as we continue on down the list of every number, no matter what number we are on our apparent list of every single number, our number that we're constructing is not in this list. Put differently, whatever number we're constructing is not in the real numbers. But that makes no sense because the number we're constructing is a real number. And therefore, by listing each one as 1, 2, 3, 4, so on and so forth, we have therefore not accounted for this number we're constructing. And therefore, we reach a contradiction because we had assumed that whatever number we end up constructing, it has to be in this list because this list accounts for every single number in the real numbers. But that assumption, therefore, is based on the fact that we can actually list, or when we list things, it's the same thing as assigning the number 1 here, number 2 here, or put differently, it's the same thing as putting the numbers in a bijection with the natural numbers. But given that this number is not in here, it means that this assumption is incorrect. What does that tell us? That tells us, therefore, that the size of the real numbers cannot be the same as the size of the natural numbers, since these two cannot be put into a bijection. We just proved this. Because they can't be put into a bijection, it means that one is bigger than the other. Logic would say that because the natural numbers is a subset of the real numbers, that the real numbers therefore must be bigger than the natural numbers. And so what we end up having, interestingly enough, are 2 infinities. I want to use equals. We have an infinity, which is what we refer to as countable. That is, we can count by listing the elements in our set. Even if there's an infinite number there, we can at least, put them in a one-to-one and list them all out. And if we had an infinite amount of space, we would be able to do that. But then we have the real numbers, which I just showed you. It's impossible to account for this number for which we're constructing. And in which case that set is what we refer to as an uncountable set. Its size is bigger than the size of the natural numbers. Why does all of this matter in the scope of applied business analytics? Because this is what we often refer to as discrete. And this is often what we refer to as continuous. And how we model things in the real world in terms of how good our results are in being able to predict things rests on how we modeled it, whether it was modeled as discrete or continuous. For example, I could model stock prices as being either high or low, or I can model them as being a specific percentage change from the previous day. Two different ways to model it, one being discrete, the other being continuous. How I model things, whether it's discrete or continuous, is going to guide how I analyze my data as well as my model of the real world. So put simply, how I'm modeling the real world, believe it or not, rests into how I'm viewing infinity. Am I viewing it as something that is countable, or am I viewing it as something that is uncountable? If it's the former, I'm going to take a lot of different types of approaches to analyze that situation. If I'm assuming or considering it to be more continuous, I'm going to take a very different approach in analysis. So coming back to the practical relevance of this philosophical discussion on number systems, because I know what some of you are thinking. This is a business analytics class. What are we doing talking about set theory? Other than the fact that set theory is used all the time in business analytics textbooks, machine learning textbooks, statistics textbooks, you name it, modeling textbooks, academic papers you read on models are going to be using this language. Not only does all of that matter, but how you model the real world in your nice, comfortable theoretical world where you can actually get results. How you go about analyzing that really depends on whether or not if you've modeled it as discrete or continuous. And for some situations, you can get very good, accurate results if you do discrete. And in other situations, you can get very much better, good, accurate results if you model it as continuous. How do you know which one to use? It's just trial and error, practice, experience. You're not going to figure out which way to model the same situation, discrete or continuous, that overnight. That's going to take a long process of you just going through one model after the next, trying to see what has worked for that situation and what doesn't. So it's not this or that sort of thing. But regardless, not going too far into a rant here, but the point being is that in order for you to understand this distinction in this modeling approach of the real world as being discrete or continuous, this rests on a fundamental understanding of, is my set of things countable, or is my set of things uncountable? Hopefully this has cleared up that matter. If it has not, I would recommend that you read a little bit more into the differences between countability and uncountability. But put simply, countable just simply means I can count it. I can put it in a bijection with the natural numbers. Remember what natural numbers represent. They represent counts. So if I can put things in bijections with the natural numbers, it is therefore by definition countable. If I cannot put it in a bijection with the natural numbers, then it is therefore by definition uncountable. What is a solid, concrete example of this? Let's look at stock price. Okay, what are all the possible prices that a stock can have? If you think about it, anybody out in the market can really put any price on a stock, even in terms of fractions of pennies. And so there's two ways to really model stock prices. I can think about it in just terms of integer dollars, right? 0, 1, 2, 3, 4, and so on and so forth. In which case I'm modeling the price of a stock as countable. Okay, countable, otherwise known as discrete. The other way is to just say that the price of a stock is any number between 0 and infinity, or if you remember this in notation, from 0 to infinity, in which case this is uncountable. I cannot list out every number between 0 and infinity. We just proved why we can't do that. You can go do that proof again in your head if you need to. Because I can't count every number in this set, in this collection of numbers, the problem is, because I can't count all of the numbers in that collection there, I have what's called an uncountable set. This is discrete, this is continuous. Depending on how I model it, my results might be good here, bad here. It might be bad here, good here. Just depends on what data I have and the particular stock itself, and et cetera, et cetera. So those are two ways of modeling the same exact thing, the price of a stock. The first way is modeling it in a discrete sense, meaning I'm only looking at the full dollar amount. I don't care about the cents. The second way is caring about the cents to a very, very granular level. Is there an in-between here? Sure. You could consider dollar and cents, and that's still countable cents into two digits, and that's still technically speaking a countable set. Would you model that mathematically as countable? No, you would actually model that as uncountable, because the math is just a little bit more elegant when it's uncountable. As it turns out, discrete, despite it being so easy and intuitive for us to understand, is very messy mathematically. And it also tends to lead us to much greater errors. Uncountability, or continuous-based modeling, is not very realistic, but at the same time, it's very elegant. The math just works so much better, and we get much better estimates for predictions. With all of this stated, this now concludes our first lecture. I hope that our discussion on countability and uncountability has not scared you away, because this is a very fascinating topic to think about, but you should at least have a fundamental understanding of these differences, because when you get to statistics, we will be revisiting this concept of countability and uncountability from the lens of discrete and continuous. And we will continue to revisit this in calculus, because in calculus, we do concern ourselves over whether sets are countable or uncountable. And in fact, calculus can be thought of the mathematics on uncountable sets. With that stated, please move on to the second lecture.